So here, as we say, the machine is something that's make the work easier. We have two types of machines. But as I said, now the machine is changed or it makes the work easier by change the size or the direction of the force. One of the example of the machines that change the size of the force, like the levers, which is a machine that has a bar. This is the bar here. There's an input force, there's an output force, and they are into a fixed point, which we called it fulcrum. And we have three types of levers: first class, second class, and third class. And the second type of machine that's here, it's changed the direction of the force, which we called it a pulley, which is a simple machine that has a wheel over a rope. Let's now start with the first type of levers here, which we called it first class lever. This first class lever, that's mean the input force, or sorry, the fulcrum point or the pivot point here, this one, is between the input force and the output. So the fulcrum here is between the input force and the output force. This is, we call it first class. Here is the input. Here is the output. So the fulcrum is between the input and the output. And we say that we have many examples for it, like the seesaw. Here, this is the fulcrum, there's the input, and this is the output. Here is the top of the hammer. Here is the oars, and here is the scissors. Now, mechanical advantage. The mechanical advantage here for the first class, it could be equal 1, it could be greater than 1, and it could be less than 1. Now, before that, what is the mechanical advantage? As we said yesterday, the mechanical advantage is the output force over the input force, or the input distance over the output distance. For the first class, they found that the mechanical advantage for it, it could be greater than 1, equal 1, and less than 1. But when they are equal, when they are less, when they are greater, depending on the location of the fulcrum. If the fulcrum is close to the load, if the fulcrum is close to the input force, if the fulcrum is between them, that means the mechanical advantage will be changed. Look at the example of the first picture here. Here the fulcrum is closer to the load. It's not in the middle, it's closer to the load. Since now the fulcrum is closer to the load, so the mechanical advantage will be greater than 1. But in the second picture here, the fulcrum is exactly in the middle. So the mechanical advantage will be 1. And in the third picture here, the fulcrum is closer to the input force, so the mechanical advantage will be less than 1. So when the fulcrum is closed, will be get closer to the load, it will be greater than 1. It will be 1.5, it could be 2. And as an example here, if you have this one, if you have here in the input force, here if you have the load. Now, when it is farther from the load, so it will be less than 1. When it is in the middle, it's equal 1. And when it is get closer to the load, the value will be increased to be greater than 1. It could be 1.5.
Closer to what, teacher?
Sorry?
Like, when is it greater than 1?
When it is closer to the load. And if it is here, like as an example, the fulcrum will be here. And as an example, like this here, like this. This is the load, and this is the input force. Where's the middle of the bar? It is here.
It's so because the distance decreased, so the force has to increase?
Yes, that's it. The input distance over the output distance. How to find it? This is not, I'm not asking you about it. Just here as an example, where is the where is 1, where is greater than 1, and where is less than 1. This is for the first class. Do you have any question here?
No.
No, teacher, thank you.
No. The load of the, now here for the second class level. For the second class now, here, now let's look at the first one. The first one is the fulcrum between the load and the applied force. Here is no. Here is the load is between the applied force and the fulcrum. The load is between the applied force and the fulcrum. This type of lever, we call it second class. Let's see the examples, like the wheel barrow. Look here. Where's the fulcrum? This is the fulcrum. It is here. So this is not a first class. Look at the load. Since the load is between the fulcrum and the effort, so this is the second class. The load is between the fulcrum and the effort. Other example, like the bottle opener. This is the fulcrum here. Do you imagine it? You applied a force on this part here. When you apply the force on this fulcrum point, the load will be, or the output force will be here, and the bottle will be opened. So this is the effort that you applied by your hand. This is the fulcrum point. This is the fixed point. When you apply a force here, the cover or the bottle will be open. So the output force will be here. So the load here is between the fulcrum and the effort. So this is an example of the second class lever. Now, let's see what is the mechanical advantage for it. Here, the mechanical advantage greater than 1. It's not like the first class, it could be greater or less than or equal. Here, it's must or it's only greater than 1. As you see in these two examples here, for the bottle opener and for the for the wheel barrow. Here, the mechanical advantage is greater than 1 because the closer, since the things that's closer to the load is what is the fulcrum. Now let's remember here, I told you that when it is the mechanical advantage greater than 1, when there's a relation between the load and the fulcrum. If the fulcrum is near the load, so the mechanical advantage will be greater than 1. And here also in the second class, since the load, or since it is like this, and the fulcrum point is here, and the load is here, and the input force is here, and as I told you, there's a relation between the load and the fulcrum, that when the load is getting closer to the fulcrum, so the mechanical advantage will be greater than 1. So in this case, we have only one situation, that the load is between the input and the fulcrum point. And the load is that the load is closer to the fulcrum, so it must be greater than 1. Is it clear?
Yes.
Yes.
Now
teacher.
let's talk about the third class. The third class here, that's the applied force now is between the fulcrum and the load. On the first one, we have the fulcrum point is between a load and the applied force. This is number 1. In case number 2, here is the pivot point, and here is the load, and here is the applied force. So now what is in the middle? The load. So this is, we called it case number 2. So if the fulcrum is in the middle, this is case number 1. If the load is in the middle, this is case number 2. And if the applied force in the middle, this is case number 3. And here we have the fulcrum, and here we have the load. So if the applied force is between the fulcrum and the load, this is, we called it the third class. Let's have an example here. Now, can you imagine what the mechanical advantage will be? It will be equal 1, greater than 1, or less than 1?
Less than 1.
It will be less than 1 because the load is not closer to the fulcrum. It's farther away from the fulcrum. So the mechanical advantage will be less than 1. Let's have some examples here. Like lifting a dumbbell. Here. This is the load. This is your hand here. Okay, you want to lift the dumbbell, as you see. So here, this is the fulcrum point. Oh, sorry, this point here. It is your muscles. Now, the efforts that you apply it is near to your muscles and near to your bones here, and this is your muscles. And the load now will be now. So the load now is, the applied force is between the load and the fulcrum. Another example, when you sweeping the leaves. Here is also, this is the, where's the fulcrum point? Here this is the fulcrum point. Here you move, here's the load will be, and here is the applied force that you apply it by your hand. And another example, or the third example, is the fishing rod. This is the, when you want now here, this is the fulcrum point, this is the force that we applied by your hand, and this is the load. And the applied force is between the fulcrum and the load, so this will be the third class lever. Now let's see what's the mechanical advantage. As we said, it is less than 1. Because, as we said, because the load is farther away from the fulcrum, so it will be less than 1. Or another explanation, because the force is decreased. So when the force is decreased, the distance will be increased. This is another explanation. As you see here, this is the hammer here. That's when you push, you apply a force. This is the orange triangle here. This will be the pivot point. This will be now your applied force. And this is here the output force. This is another example of the third class. Here's also, this is the pivot point. This is the applied force, and this is the load. The applied force is between the fulcrum and the load, so this will be third class example. So this is for the lever. The lever, as you see, is changed the size of the force. The size of each force here, if you choose any machine, it will be less than if you use it with your hand, or without machines. Now we have this one of the example lever. Lever change the size of the force. We have 3 types of levers. The first class, where the pivot point is between the load and the applied force. The second class, where the load is between the fulcrum and the applied force. And the third class, where the applied force is between the load and the fulcrum. Now, if you hear, so let's make here, let's now contrast between them. So the first class. second class, and the third class. Now, for the first class, as we said, the fulcrum point is between the input and the output. On the second class, the output is between the fulcrum and the input. And the third class, the input is between the output and the fulcrum. Now, the mechanical advantage for the third class is less than 1. For the second class, it will be greater than 1. And for the first class, we have 3 situations, according or depending on the distance or on the position of the load. The mechanical advantage, it could be greater than 1. The mechanical advantage, it could be less than 1. And the mechanical advantage could be equal 1. So when the mechanical advantage will be greater than 1, 2 situations. If we have the load is between, it's greater than 1, we have 2 situations. If the load is between the input and the fulcrum, or if the load is closer to the fulcrum, we have the mechanical advantage is greater than 1. Now, when the mechanical advantage is less than 1, two situations. Case number 1, when the fulcrum point is closed to the input force, or when the input force is between the fulcrum and the output force. And when the mechanical advantage is equal 1, only one case. If the fulcrum is in the middle between the output and the input force. Is it clear?
Teacher, can we do some examples on this?
Yes, teacher, please.
On what?
Like between the second type and the third type, like I might confuse myself. So if I see more examples.
Yeah, like to compare them.
Yes.
Teacher, like in the quiz, are you going to ask us if this is the first class or second class?
Yes. You have to think now, where's the fulcrum point? Where's the load? Where's the input force? And then you ask yourself, if it's the load is near to the fulcrum, or the load, sorry, between the fulcrum and the input force, this is second class.
So, teacher, is there any problem solving about
No.
this?
Just there's no, yeah, I mean solving math, you mean?
Yeah.
No, just explanation.
Oh, okay.
This one was called torque. This the fulcrum and the lever, and there was a law for it, but we're not taking it.
Yeah, we inshallah we're going to talk about it in chapter torque. I think chapter 13 or chapter 10. I forget, but yes, we are going to talk about the torque also.
Oh, great!
Not in
Then
this chapter. Next chapter, inshallah. So now, shall I repeat these examples or give you another examples?
I think another example, or
Yeah,
whatever works with the girls.
So
It's okay with me, teacher. We can explain this again.
So I will let you, maybe if you see the videos, maybe you.
Okay, so teacher, in this lesson, like we just should know about the types and if this is the input or output, right?
Yes, you have to know where's the load, where's the input force, where's the fulcrum, and then guess if it's first class or
Teacher, the
second.
load is the same as the output, right?
Sorry?
The load, it's the same as the output, like the results.
Oh, yes.
Okay, thank you.
Now, here we have many videos.
Forms of a machine. I'm Chris, and today we will be talking about levers
Did you
and
hear
how
the
we
voice?
use these levers in everyday life and inside of our bodies to produce movement, increase force,
Yes, teacher, we can.
functional changes.
Yeah.
Levers are one of the simplest forms of a machine.
I hope
A
this video
lever is a
gives you
simple
more
machine that
examples.
allows you to gain a mechanical advantage in moving an object or applying a force to an object. A lever is a simple machine that consists of 4 parts. The first part is the fulcrum, known as the pivot point, axis, or balance point. The second part is the resistance, or load. The third part is the effort force. The fourth part is the lever arm, which can be divided up into 2 parts. You got the force arm and the resistance arm. Now, the main function of a lever is to gain a mechanical advantage in moving an object or gaining force. Mathematically, the mechanical advantage is determined by dividing the force arm by the resistance arm. An equilibrium is achieved by effort times force arm equals resistance times resistance arm. So if the resistance and effort are the same weight and same distance from the fulcrum, nothing will move. We'll be stuck in a stalemate, like 2 twins sitting on a seesaw. So let's go over the 3 types of levers, and then at the end we will go over how we use those levers in the world around us and inside of us. There are 3 types of levers. First, we will look at the first class lever. It's set up with the fulcrum in the middle with the effort and resistance on the sides. The function of this lever is to change directions. The mechanical advantage can be less than or greater than 1. If you recall, you can determine the mechanical advantage by dividing the force arm by the resistance arm. A comparable real-world item would be the seesaw, like the ones the twins are sitting on. So again, the fulcrum is in the middle, with each twin acting as the resistance or effort force, depending on which one is changing directions. For example, let's say that the twins on the seesaw had different diets in life. One lived off of Oreos dipped in grease, and the other ate nothing but veggies. So we have Patty McFatty at 200 pounds, and Skinny Sarah at 100 pounds. In order for Sarah at 100 pounds to move Patty at 200 pounds, Sarah would have to increase her mechanical advantage greater than 1, at least 2 times the distance from the fulcrum. And on the other end, Patty would have to decrease her mechanical advantage to less than 1 because she has twice as much force than the resistant. Understood? Good. Moving on. Next up is the second class lever. It's set up with the resistance in the middle of the effort force and the fulcrum. Its function is to increase force with the range of motion being sacrificed. The mechanical advantage is always greater than 1. The common real-world item that uses this lever would be the wheelbarrow. The wheel is acting as the fulcrum, with the rock being the resistance in the middle, and the effort force would be the human carrying the thing. Mechanical advantage is always greater than 1, because the force arm is always going to be longer than the resistance arm. This allows you to increase your force produced. However, you end up lacking range of motion with this lever. Imagine this rock weighed 100 pounds, and the force arm is twice as long as the resistance arm. The 100 pounds would feel like 50 pounds. If the force arm was 4 times as long, the 100 pounds would feel like 25 pounds. However, the longer the force arm, the less range of motion you will get. This is an example, by the way, and probably not to scale, so put your measuring tapes away. Now on to the final lever, the third class lever. Effort is located in the middle of the resistance in the fulcrum. The function of this lever is to gain distance, with the mechanical advantage always being less than 1. The common real-world item that you'd be using every day, depending on your appetite, would be the hot dog tongs. With the force arm being shorter than the resistance arm, the fulcrum would be where the tongs are connected. The effort is applied to the center of the tongs, with the hot dog being the resistance. The third class lever is actually the most common used lever in the human body. Okay, now I'm going to give you a free quick tip on remembering which lever is which. And that is the word free, with 1 E, not 2. Spell it out, F-R-E. The first class lever is the F with the fulcrum in the middle. The second class lever is the R with the resistance in the middle. And the third class lever would be the E with the effort in the middle. You're welcome. Now for some examples of the levers in the human body. The first class lever would be the human head sitting on the spine. The fulcrum would be the middle of the spine on the atlas. The neck muscles would be the effort force, and the weight of the head would be the resistance. The function is to change directions, so when the muscle contracts, it creates force, causing a change of direction. Okay, now, next is the second class lever. We use the second class lever in the human body to raise our heels off the ground. The resistance is in the middle with your weight of the body. The fulcrum would be your toes, and the gastrocnemius muscle, your calf muscle, would be the force. There you go. It's just like a wheelbarrow. Your toes are the wheel, the weight of the body is the rock, and the effort force is, well, it's you. Now on to the last lever, the third class lever. This is the most common lever in the human body. The brachialis muscle will be an example. This is the third class lever, so we know that the effort force is in the middle. This is where the brachialis muscle inserts, and that is our effort force. The elbow joint would be the fulcrum, and the resistance would be the hand or whatever the hand is holding. Those are the simple machines known as levers that are in the world and in your body. Please like and subscribe to my channel, and you can become my best friend by following me on social media on any of these 4 sites. You can become a Patreon and help support me to make more videos in the future. Until next time, as always, happy studying, my friends.
Did you get it clear now?
Yeah.
Yeah, it was a nice video.
Yes, teacher, thank you.
Yeah, welcome. Did you find how the physics can explain the other sciences, the other type of sciences? This is in biology, is in our hand. We have physics in our body.
I found it really nice that he included biology in explanation of physics because it's
Yeah, me-
interesting.
Yeah. Now, actually, we have 2 minutes left, so I will not start with the police. I will keep